Good afternoon. It is 2:45 in Philadelphia, and welcome again to Thermal Live 2016. I'm Graham Kilshaw with Electronics Cooling Magazine, and we are the creators of Thermal Live. This presentation is brought to you this afternoon by Mentor Graphics. Our speaker is John Wilson, and the topic is increasing product reliability with automated thermal model calibration. John is the electronics product specialist at the Mechanical Analysis Division of Mentor Graphics. Good afternoon, John.
Hello, good afternoon. Good morning.
Good morning, still in California, yes, or wherever you are in the world. John's joining us from Fremont, California. We're also joined by the senior editor for Electronics Cooling Magazine, MP Divakar. Welcome again, MP, from San Jose.
Sure, thank you. Good morning, good afternoon, and good evening to all. I know we have a worldwide audience, so I'm really happy to be taking part in this.
We have quite a few people logged on listening live now. Welcome to you wherever you are in the world. If this is your first visit to Thermal Live, let me introduce a few of the features of this platform to make your presentation experience a little better. You can pose a question at any time during the presentation. Simply click on the Q&A box at the bottom of your screen. We'll collect all the questions during the course of John's presentation, and then we'll do our very best to answer them at the end. Should you have any technical issues, please simply refer to the yellow tab on your screen, which lists many of the common issues that are sometimes experienced with webinars. You can also chat with other audience members if you want to see who's here and listening to this particular presentation. Just click on the group chat and pose a question there. But that group chat button is only for group discussion, not to send questions to the presenter. You can click on two different links at the bottom of your screen. One of them, if you hover your mouse over it, you will see it will take you to the Thermal Live website, where you can still register for the remaining presentations tomorrow. I believe we have 10 presentations over the course of these 2 days, so don't miss on anything that's still coming. The second link you can see at the bottom of your screen will take you to the Mentor Graphics website, so take advantage of those. I can already see some people asking, can they download the slides from John's presentation? You can, but not yet. The slides will be available in 24 to 48 hours after the presentation today, and you'll automatically be sent a link that you can access the slides from there. The video, however, if you would want to re-watch the presentation, will be available within an hour or two of this presentation ending. So we hope you enjoy the presentation. And with that, I'm going to hand over to John Wilson.
Okay, great. Thank you. Yeah, so today I'll be talking about increasing product reliability with automated thermal model calibration. So specific topics that we'll talk about are...
Just as I put it down, he went quiet.
Hello? Yep. Sorry, I'll continue on. So the motivation, why are calibrating components important? And we'll also compare the calibration process. I'm going to compare kind of a historical calibration process with a new process that involves transient measurement. And then we'll show a calibration example, both to show kind of the workflow and also some of the benefits you get from this calibration process. So the motivation. So calibrating thermal models to match transient measurements is critically important for modern electronics thermal design. So the type of calibration I'm going to talk about is for transient measurement. And a lot of today's electronics are put in systems that are both dynamic and unpredictable. So it's important to use calibrated models that are calibrated against transient measurement. You know, the whole goal of using models, period, is so that we can shorten the design cycle, build better products, more reliable products. if they're placed in dynamic environments, we need to calibrate these models against a dynamic or transient test. And we want to maximize model accuracy, certainly. So the risks of not designing with an accurate model, first, if you don't know that it's inaccurate, then this could lead to reliability issues. If you recognize that the models you're using are inaccurate, then that could lead to over-design. Either way, it's going to lead to longer design cycles because the model that's used to design with doesn't match the measurement results at the end. So you're going to have to spend time at the end of the design process, kind of correlating and understanding the differences. Also, calibrating all model aspects for all package time constants ensure the package will respond accurately for any steady state or transient application. So we're talking about calibrating against a transient test to develop models that will be accurate for any unforeseen or environment or powering profile. And we say that relying on single metric type data is not enough. So typical JEDEC data that we see, theta JA, theta JC, theta JB, certainly are risky to design with at some level anyway, but certainly not adequate for designing for products that are time dependent. And it's also vital to demonstrate the accuracy to ensure informed design decisions are made. So if we calibrate a model against a metric, then I think we have some confidence that if the system matched the test setup, that we would have accurate results. The reality is that we need to be able to take the calibration environment and extend that to unforeseen system environments. And that's very difficult to do if you're just using this metric type data. So we need to be able to develop models that would be valid for any unforeseen environment. And if we could do that, if we can build a model that is accurate for any power and profile or environment and demonstrate that accuracy, that could lead to a certified supply chain for thermal models. So we can have confidence that if a vendor provides a model to a system integrator, that both parties are confident that model is going to be accurate and that there's evidence that the model is accurate. Okay, so certainly motivation, we want more accurate models. If it can be a repeatable, scalable process that we can demonstrate the accuracy, then that could lead to a consistent methodology and approach to providing models. So let's compare two processes, kind of the historical process, the way I see it, and this process that would involve the Fluotherm and Tristor, which is an automated process. So the process is going to start, in either case, with an experimental measurement. Typically, an experimental measurement would be taken at steady state at discrete points. So thermocouples placed on the package or at discrete locations inside, say, a heatsink base, what have you, but taken at steady state. With this process, the Tristor process, it's going to be, Tristor captures the transient thermal response. And we're going to talk more about the Tristor measurement a little bit later. But one case, it's steady state measurements. The other, it's a thermal measurement we need to calibrate against. The next step of the historical process is to build an analytical model that replicates that experimental measurement setup with the best known values, so assumptions based on material properties or contact resistances, interface material resistances. Okay, with the Fluotherm process, it's a little bit different where I can identify these somewhat known values. The calibration process, I would characterize it as a process of quantifying uncertainties. So with the Fluotherm process, we can both build a model and identify the range of unknown values. So I understand, that the active area of the die is something I'm not sure of, so I can put in a lower bound and upper bound while I'm constructing this calibration environment. The next part of the process for the historical process would be to simulate it, inspect the results, and determine how to modify the baseline model to better match the results. So this process would loop around continuously until either one or two things could happen. One, you match your experimental measurement, or two, what often happens, I believe, is that you run out of time and you rationalize that the model is good enough. The reality is that even if you calibrate against this steady state setup here, it's only going to be valid for steady state design, and typically only valid with any degree of accuracy for systems that kind of replicate the experimental measurement setup. So with the flow-therm calibration process, it's an optimization. So it's a design of experiments and optimization process that calibrates against the Tristor measurement results. So in the end of the process, you have a fully calibrated model and a provided degree of accuracy of that model. So it's a scalable, repeatable process. At the end, you have a calibrated model within a quantified degree of accuracy. So let's talk a little bit more about that process. So the process starts with the Tristor experimental measurement. And if you're not familiar with the Tristor, that's use the electrical test method. So no thermocouples are involved. You are electrically connected to the device. And what you're measuring here is the voltage drop across the temperature-sensitive parameter. Once you understand that correlation between the voltage drop of that temperature-sensitive parameter and temperature, and perform the measurement, which is taken between two power states, either a high power stepping to low power or low power stepping to high power, and you take results across that transient response. So in the end of that test, what we're going to get is a temperature versus time curve. So both your analytical model and these measurement results can produce temperature versus time curves. The next part of the process, which is an important part, is to take that temperature versus time information and convert that to a structure function. One way to think about the structure function is the RC path, the resistor capacitor path, that the heat takes from the junction to the device and to the ambient. So on the horizontal here we have thermal resistance, vertical is thermal capacitance. The lower left would be the junction of the device, and we step through the stack up of the different materials and see the slope changes here and the individual thermal resistances and capacitances associated with that layer, all the way through to the ambient, which could be a cold plate or just the ambient air. In either case, that the ambient has infinite capacitance. So that's fully captured the thermal path along that package. So this is what we want to calibrate against. Okay, so from the analytical side, we would start by building a model that replicates that test measurement. And here we're looking at a flow-therm model that's a transient model that is going to predict the temperatures as a function of time. And this is built based on our best known input values. Like I said, calibration involves quantifying uncertainties. So in this example, the somewhat known values are the die solder conductivity, and we're going to put in ranges, a lower bound and upper bound for these somewhat known values. In this case, conductivity of 20 to 45 watts per meter Kelvin. The source size, we're not confident we know what the active area of this die is, so we're going to vary the size in the X direction and Z direction. So X size varies from 4 to 7 millimeters, Z size 8 to 11.5 millimeters. Okay. Oops. Okay, so the actual calibration interface, I just wanted to point out some of the important factors that are involved in calibrating an analytical model to the measurement results. So certainly we want to be able to import the measurement data and define the temperature to calibrate. So our analytical model is a full field of temperature, so we have to identify what temperature we're going to use to calibrate against the measurement. So this is typically an area or volume of average temperatures on the active surface. It could be a point measurement that you could use. Typically, it's a volume. So we identify that area that we're going to use as our reference temperature to calibrate against. Next, we can identify the values that we're uncertain about and the range that we're going to study those values within. Third, we want to make sure that the analytical model is the same as the measurement model or measurement setup. So the power, the duration of the transient, and the initial temperature. And then how many experiments to design? So in this case, I think it says 50. And the calibration extent. So let's take a look at the plots that are shown here. In the upper right, we have the transient thermal resistance curve, both of the Tristor measurement and the baseline flow therm analysis. And the lower area is the structure function for both flow therm and Tristor. The calibration extent is, as we remember, the left-hand area is the junction, and as we move to the right, we get to the environment. So if we want to just calibrate the package, then we don't want to calibrate the full extent. We can cut off and say calibrate up until this thermal resistance. So that's shown here as a vertical line, up here as a horizontal line. Okay. So there's just some of the important factors when you're calibrating against a measurement, transient measurement. Next, let's just take a look at the design of experiments. I like to show this because it illustrates the number of simulations that are created, with a couple of clicks of a button, and the distribution of those inputs. So we get a large amount of data, impossible to interpret that, at least for me to interpret that, but we get a lot of information to leverage for our optimization. So once we've designed experiments, we can optimize and calibrate the results. So for each one of those designs, we're taking a look at the structure functions and the transient thermal resistance curve, and then flow therm will identify what is the optimum. So we see a nice correlation between the structure functions of both flow therm and the Tristor measurements. But the optimization does more than provide the optimum. It provides you the ability to understand the sensitivity of your design inputs to the cost function, in this case, the calibration curve, the structure function. It could be that we've chosen some inputs that are not really relevant for optimization. So with the design of experiments, we can understand the influence of each one of those inputs. So in the end, if you take that initial baseline model and the calibrated model and place it into a system environment, we'd see the difference in peak temperature predicted. But if we take one of the kind of snapshots at 20 milliseconds, we can see the difference between the uncalibrated and calibrated model. So the calibration process is valuable for both, say, the system integrator who is designing to peak temperatures, but also the package vendor that wants to understand the temperature distribution within the package, because the distribution could affect reliability in terms of thermal stresses. So the calibration is beneficial to both. Okay, in summary, correlating a model against transient measurement provides the most accuracy. Because calibrating against transient measurement is going to be accurate for both steady state and transient or dynamic systems. We don't always have the luxury of designing to a thermal design power. We have to design to a power profile, different powering conditions, different environmental conditions, and so that we don't over-design or under-design and affect the reliability of the product. We need to really understand how these different components behave with respect to time. Structure functions help identify areas of inconsistency between the assigned model values and measurement results. So while it's possible to calibrate against the temperature versus time curve, in a sense it's kind of calibrating blindly because you don't know where the error within your model exists. So the structure function is going to help identify where in that stack up you have the most deviation from the actual measurement results. So I think the structure functions provide a lot of value when it comes to calibration. So automating the calibration process provides for a repeatable and scalable process. So it reduces the time. So it's very repeatable in the sense that we just put in the input parameters and range that we want to study and push a button, and the process will return the sensitivity of those input parameters to the thermal response and also provide the optimal solution given the inputs that you provided. Okay, thanks. I think I talked pretty fast. I hope there's some questions.
Hi, John. Yeah, very good presentation. Yeah, a little quicker off the mark than we thought. But attendees, if you have questions for John and on this particular subject, now's the time to post them. And just as a reminder, to post your questions, use the Q&A button, please, at the bottom of your screens. Now's the time to send in your questions. We have a couple in there right away, and so I'm going to pass over to MP Divakar, the senior editor for Electronics Cooling Magazine, for the Q&A portion of this presentation. MP, over to you.
Oh, yeah, thank you. Thank you, Graham. Again, it was a very good presentation. So, John, thank you for taking the time to present it to the electronics cooling audience. So we have, let me start off with an audience question from Ashutosh, and he is a little bit skeptical. He's thinking that this is just one sample. How do you calibrate this to address the batch-to-batch variation in your structure functions?
That's a good question. Right. I mean, when you take the transistor measurement results, it's an accurate enough test that you're going to be able to show the batch-to-batch variation of the component. So I guess because it's capturing that effect, it's up to the person calibrating what they want to calibrate against. Right. That's a good question. I guess I have to think about that some more, but yeah.
Well, we have a second question. What is the type of algorithm that Pfister master software uses to do the calibration process?
Well, it's our own algorithm. It's a Coward network, so it takes that temperature versus time data and does its own processing to develop a Coward network out of that response.
I see. Does it use any filtering as it acquires the data points, as you go, from one interface to the next? Because I see that in your structure function curve, as you transition, from the die, to the die attach, to the package, and and on and on. you see some, inflection points or, change in curvature, right? And how does it address those, the interpolation?
Yeah, I mean, the data is filtered. Some of the measurement data is filtered, and I'm not 100% certain on the process that it uses to develop the structure function from the measurement results, but it's essentially hundreds of resistors to capacitors that make up that network.
I see.
Yeah, there's a couple different ways to look at the data in the Twistor Master software. One is we call it the cumulative structure function, which is the structure functions that we showed, and one is the differential structure function. So you can actually identify those inflection points more precisely. But how it, if it does any special processing in those areas, I'm not sure of.
So Ashutosh has a follow-up question. Is this process, is this automatic within Flowtherm? Can you set it up to go automatically, as you drive with the Twistor system?
Good question. Flowtherm is, as Flowtherm has evolved over the last few years, more and more Flowtherm capabilities are available to access through scripting. So it's conceivable that this automated calibration process could be invoked via script. We don't have that feature yet, but it's possible. Right now, it would be a manually, there's a pull-down menu in Twistor Master to export the Flowtherm calibration model. That part of the process, could be automated. This is a fairly new process, so we haven't automated the connectivity between the Twistor Master and Flowtherm. But it's conceivable for the future that, yeah, it could be done.
Alex, from GM, he has a question on how do you account for the system startup, especially I think the power dissipation. Probably is referring to the transients.
How do you account for system startup of software power dissipation? Yeah, I'm not. So let me just describe, I guess, the measurement process. The way the measurement is typically done is first the device is calibrated at sensing current. So a very low current is applied to the package that you can measure voltage across this temperature-sensitive parameter. And you're varying the temperature of the package through an oven or oil bath or something so that you can calibrate the temperature versus voltage at this sensing current. And once you have that calibration information, you can go to the test, and what we typically do is power the package at a supply current until it reaches a steady state temperature, and then we step down to our sensing current. As soon as we step down, we start collecting information, right? We start measuring voltage. Now, and that's it's a microsecond time scale. Now, I'm a mechanical engineer. I'm not an electrical engineer, but when you switch the power, there is a period at which the voltage you're measuring really isn't based on the temperature information. It's based on just the electrical transient. So any part of this electrical test method is anytime the power changes or the current changes, there is a period at which you have to the data isn't useful. So there's different methodology, I think, spelled out in the standards on how to essentially go back to time equals zero to interpret the real measurement results to what would be having at time equals zero.
I think
hopefully that answered the question.
You answered it. I think that's what the question was. Let's move on to the next question. I think it is, this is by Matt from Intuitive Surgical. He's wondering if we can optimize against multiple test conditions, different input powers and different environmental temperatures. So I think he's trying to address what he's trying to address is to have a robust, calibrated model that is the best fit for all conditions.
Yeah, what I would do is, the twistor measurement and capturing the response for the one test should be valid for other environments. So if you have measurement results for different environments, I would calibrate with the twistor measurement against one, develop the calibrated model, and then take that calibrated model and place it in the analytical system environments and verify that it's giving the same results as the other measurement environments.
Yeah, I think I can partially see where the question is coming from. I mean, you alluded to the oil bath calibration, or the so-called K-factor calibration, right? Excuse me. It's very similar. And most of it is, almost all the time, it is pretty linear. So I think the different environmental temperature, calibration condition probably has a minimal effect. But I haven't done that. Most of my calibrations have been on the same temperature, whatever the ambient temperature is surrounding the oil bath. So I'm not 100% sure if there is a strong dependency. Anyway, let's move on to another question. HASM. So how do you compare a detailed model, especially from a CFD tool like Flowtherm, to a thermal network model where the temperatures are integrated spatially?
I'm not sure.
More broader question, yeah.
Yeah, I'm not sure how to do that. I mean, right. I guess I would have to know more specifics about this to be able to provide any kind of sensible answer. Yeah.
I imagine, I think by the thermal network model, he is referring to, the RC network, where you have each resistance modeled separately, and then lump the capacitance model, thermal capacitance to that, and then you build this grid work for your entire geometry, and you can use a finite difference technique to solve that. And how do you calibrate that against Flowtherm? If I understand correctly, that's what the question is alluding to, but I'm not so
right.
So HASM, if you want to ask a follow-up, please do. You can try. Let's move on to...
Okay, let me just say that, yeah, there's a big gap in, compact thermal models in that, probably the most accurate kind of standardized compact thermal model out there is a Delphi, compact thermal model, but that doesn't support, capacitors. So there is no kind of methodology that would allow a multi-resistor and capacitor type network. So, right, this is even with the twistor, you can export a dynamic RC network model to Flowtherm, but it's not really like a multi-dimensional, let's say. It's two-dimensional. It's like 1D, up and down, essentially. But, if you have a lot of spatial variation, I'm not aware of any kind of adopted approach to that or methodology,
Okay. Yeah. I think, HASM has qualified that with a follow-up question. He's telling us that the thermal network model is the RC model for the structure function.
Yeah, right. So yeah, the structure function, you can get a compact model directly from the Twister Master software, but it's really only suited for 1D heat transfer, actually one heat transfer in one direction. So if you're taking a measurement result, say you're taking a Twister measurement, the only power you know is your input power. So if you're developing a thermal resistance, you need to base it on the input power. So you want to have confidence that you know where that power is going. So that's why typically measurements are done with a heat sink or a cold plate where we know the heat flow direction because we're going to base all the thermal resistance information on that. So like I said, so if that condition is true, then yeah, we export a compact thermal model directly from the Twister software that can be used. We also export, SPICE models. So you can get a network model directly from the software, but it doesn't support, there's no, kind of procedure in place for capturing a 3D type effect.
Next question, I hope I'm pronouncing the first name correctly. It's Johanna. How do we manually import the empirical calibration, test results into Flowtherm for the development, creation and development of an analytical model?
Right. So with this process I described, there's a specific file exported from Twister Master that's read in. So any kind of, if you were to do this process with an analytical tool, Flowtherm or otherwise, manually, you would need to, if you want to use structure function, you need a way to take temperature versus time data and process that to form a structure function and develop a cost function, something that is you're going to use to match that curve against the measurement curve. Flowtherm, I'm sure other tools too, can be automated so that you can script different models. So you would just need some external type of process to. It's just when you calibrate against transient test data, it's the difficulty increases probably at least 5x versus a steady state calibration. So once you have the temperature versus time data, we're not comparing a point value. We're comparing point values, let's say, at various time increments. Gee, I guess you'd have to give a lot of thought. It could all be manually automated, to kind of correlate a analytical model against measurement, but just probably a lot of work.
Okay. One more follow-up from Hazem. He is alluding to the Foster thermal network, the so-called pi model, behavior model. It seems that does take into account the 3D effect, the thermal crosstalk, if you will, effect.
Right. I think that I think you could develop a network that captures that. Certainly, there's just no kind of agreed upon or a typical way to take a model like that and everything would have to be kind of done in-house, and you would have to come up with a network and topology as far as surface areas exposed to the environment, the network topology that matches your measurement results, and then you would have to have a set probably of measurement results that kind of capture the intent that you're trying to get that compact thermal model to replicate. So I don't know that it's a deficiency in the network approach. It's more of a process. what input from measurement are you going to use, so what measurements you have to perform. And actually, I guess once you have a calibrated model, then how you're going to exercise that detailed model to develop a network model that provides the same results. So I think the network is okay, either approach, but a lot of work, I feel.
Okay, I think we've come to the end of Q&A. Just a reminder to the audience, the recording will be made available later in an email. You'll all receive an email notification. We've had a great day of presentations on Thermal Live, day 1. We got a whole day chock full of more interesting presentations. Come forth. I encourage everyone in the audience to sign up. You'll find links below the screen. Graham, you have any closing comments for today?
No, I think yourself and John have had a very interesting conversation. I hope all of our readers have enjoyed it. And I would just say, check out the program for tomorrow. There's more great content to come on Wednesday.
Okay,
with that,
go ahead, Graham.
MP, you want to wrap up for us?
Sure. I certainly would like to thank our speakers for the whole day. We had many interesting ones, and quite a few of them were enlightening ones. Definitely the audience, the Q&A from the audience and the interaction has made it worth every second of it. I myself, this is my first time hosting along with Graham and Item Media. It was a very enjoyable and rewarding experience. Definitely looking forward to tomorrow and interacting with the audience again. Again, good day to all who tuned in. So don't forget to sign up for tomorrow's Thermal Live.
And thanks to John and Mentor Graphics too. Excellent presentation.
Yeah, thank you.
Thanks, and have
See you tomorrow, folks.